All right, everyone. Good morning, and thanks for attending my talk. My name is Moritz Jodeit, and I'm going to talk about how to hack video conferencing systems. So specifically, I'm talking about our results of a research project where we conducted research on Polycom equipment. The structure of the talk basically reflects the systematic approach we followed when doing the research. So basically, we start with knowing nothing about those devices, and we conclude with the ability to remotely compromise them. So we start with taking a look at the attack surface, basically the network-based attack surface. Then we'll start analyzing the firmware update files, which allows us to get some information about the innards of those systems. And then we take a look and basically find several ways to root those devices, because usually you don't have system-level access, but we want to have that in order to conduct our research. And finally, once we got root access to the device, we take a look at the system from the inside. So we take a look at the system architecture, but mainly from a bug hunter's perspective. So we are taking a look at all the major processes and stuff like that. And after doing that, we built a vulnerability development environment, which basically means we set up remote debugging, which allows us then to more easily find bugs and more easily especially write exploit for that. And at the end, I will show you an exploit we did for one of the vulnerabilities in the H323 stack, which basically gives you remote root access to the device. And since having root access is nice, but what we actually want to do is we want to take control over the complete device, so making use of the peripherals like the camera and the microphone. So in post-exploitation, I will talk a little bit about what we did in order to implement this functionality in our payload. So a few words about me. I'm from Hamburg, Germany. I'm a security consultant at Enruns, and mostly I'm doing application security, so stuff like reverse engineering, writing exploits, basically finding bugs in source code, binary code, stuff like that. I did some previous research on USB security in the past, and in general, I like bug hunting, so that's probably the reason I'm doing all of that. So first of all, why I'm interested in video conferencing security. I mean, first of all, those devices could be considered just another embedded device, which sometimes is connected to the internet and also some kind of internal network. So an attacker could use them as a kind of hopping point into your internal network. But more interesting is the fact that most people use those systems to exchange critical information. So critical meetings might take place, for example, over such a system. And if you are able to attack those systems and compromise them, you could sniff all of that, which might be interesting. But even if a company, for example, has some kind of policy in place which prevents you from exchanging sensitive information, these kind of devices, especially the higher priced ones, they are typically installed at locations which are pretty critical, like the boardroom of a company or the major conference room. So even in those cases, if I managed to exploit one of those devices, I could listen into conversations taking place in that room. I could use a camera to look around. Maybe I find some paper lying on somewhere. And on the other hand, these devices are typically used in large companies, like, for example, a lot of banks are making use of video conferencing. Insurance companies, governments make use of it. And sometimes even hackers, because beginning of last year, H.D. Moore published some research where he basically was scanning the internet and he found several video conferencing systems which had the auto accept call feature turned on. So this allows you to basically just connect to the system and your calls automatically be accepted. So what you can do in that case is you basically can join any conference. You can listen in what's being said. What I was thinking about that is, of course, it shows that there is that many people really don't think about when they connect those systems to the internet. But this is all stuff which can be hardened by, for example, firewall rules, or you could harden the configuration. So I was more interested in what you could actually do with those devices when they are really in a hardened environment. So, for example, when all the administrative interfaces are blocked, when all the configuration settings are set to their most secure default or to their most secure values. And as it turns out, it's still possible to break those devices remotely, even in such a case. And even in the case when the call auto accept feature is turned off, which I will show during my presentation. So first, some background about video conferencing. So everybody knows video conferencing is about exchanging voice, audio, and sometimes even data about packet-based networks. And packet-based networks means, in most of the cases, either IP or ISDN. Which is interesting because there are some systems which are connected to both. So there's one attack scenario where, for example, you could use the telephone network to compromise such a device and then jump onto the IP network and basically get access there. And basically, there are two kinds of video conferencing systems. So there are dedicated systems and there are desktop systems. While desktop systems are typically the lower priced ones, and dedicated systems are the higher priced equipment which we are interested in. So just to give you an idea about the main players when it comes to video conferencing. So as you can see, the major players are Cisco, which is also known as which was also known as Tandberg, and Polycom. And then we have some smaller players like LiveSife, Teleris, Video. In order to do research, initially our plan was to do some kind of a market comparison. However, due to time constraints and some kind of problems getting the hardware, we actually decided to just choose one of them, which happened to be Polycom. So Polycom is, I would say, one of the leading vendors, and they offer different solutions. And most of the solutions, or many of them, are actually pretty expensive, which is interesting for us because that means that the target companies and organizations are mostly large ones. And if you take a look at their website, it's pretty impressive. So you find a page of their customers, and it's basically all the Fortune 100 companies, including governments, banks, basically every juicy target you could think of. So to do our research, we used a Polycom HDX system. So the HDX series of devices is probably one of the devices which is really popular, and there are several configurations, and we happen to have a HDX 7000 HD, which you can see on the right, which comes with some nice peripherals, like, for example, the Eagle Eye HD camera, which is a pan-tilt zoom camera. That means you can remotely control that camera. It comes with a Mica microphone array, which is a 360-degree microphone, which can pick up voice from really far away, and some remote control, and the whole thing is then connected to some external display. So after having the hardware and basically knowing nothing about those devices, we first of all define the attack surface. So we take a look at what network-based attack surface we have. So we don't consider physical attacks at this place. So the first thing is, of course, the Polycom web interface, which is the main interface to configure those devices. So you basically can configure every aspect of the device. You can do some diagnostics with it. And of course, it could be attacked in theory. Those devices have some kind of provisioning mechanism, which allows you to remotely apply updates and do configuration changes. Additionally, there are two command line-based interfaces. The first one is the API interface, which is mainly used by system integrators to configure the device to work with external hardware or with third-party hardware, like, for example, crypto accelerators or crypto devices. The Polycom command shell is comparable in functionality with the Polycom HDX web interface. but it's completely command line based. And of course, those are interfaces which could be accessible on the network, so you could, in theory, try to exploit those. Those devices have SNMP enabled. However, SNMP write access is not supported at all. So, of course, you could still find bugs in the SNMP stack or implementation, but especially from an aspect where you change certain settings through SNMP, it's not that interesting. And finally, we have video conferencing protocols, which is interesting because this is one part of the attack surface which can't be disabled. So if you want those devices to make actually video calls, one of those protocols, either H323 or SIP, must be enabled. Otherwise, you can't use the device, right? So we'll see later that those protocols are pretty interesting when it comes to exploiting those devices. So we basically start with some firmware analysis because this is one thing we can analyze and take a look at without having root access to the device. So if you go to the vendor webpage, you will see that you can get software updates at support.polycom.com. And every software update is basically a zip file. And each of those zip files contains a single pub file, which stands for Polycom update file. And those can be either applied through the Polycom web interface, or you just use this provisioning mechanism to apply those. And all of our analysis, which I'm presenting now, is based on version 3.05, which was the current version when we did that research. So if you take a look at the pub file structure, it actually doesn't look too bad, right? So you at least have some strings somewhere in the beginning. The first few bytes kind of look like a file signature. So we started analyzing the complete file format, and it turns out it's pretty simple. So it consists of a pub file header, which are the first 768 bytes, and then there are two packages or two archives. So the first one is a bootstrap archive, which contains basically code which is used to install the update and extract the remaining part of the update. And the more interesting part is the update package at the end, which is the archive which contains all the files which are updated. So if you don't have access or don't have system-level access to the device, this is actually the archive where you can find all the files which, in theory, are also running on the device. So in the next step, what we did is we wanted to find out the exact format of the pub header. So what you typically do is you try to guess certain fields, you try to compare different versions of a firmware update file in order to find out the complete structure. However, in this case, it was much easier because, as I said, there's this update package. So we were looking around trying to find interesting files, and we found a file called pubutils ppc, which is a PowerPC binary. And this binary is called the Polycom update utilities. So it's actually the binary which is running on the device, which is responsible for verifying the integrity, for installing the updates. And of course, such a binary has all the information about the format of those pub files. So it was quite nice to find this binary. And additionally, what you can do is you can take that binary and run it in QEMU. So we just installed just a normal Linux system in QEMU, and we were able to run this binary. What's interesting is, if you take a look at the usage information, it's not only used to verify and install updates, but it's also used to generate updates. So, for example, you have a command generate, or you have a command gen keys. So it looks like this binary is actually used also by Polycom to generate update files, which is interesting because it's shipped with every device to every customer. So we reverse engineered that binary to find out the exact format of the header format. And so it turns out the first few bytes are really a signature for the file, which can be either PPUP or PPDP. And then the remaining header consists of several fixed size fields, which are padded with null bytes. So this is the complete structure, which we figured out. And it contains several interesting fields, like some information about hardware. So it specifies where the update can actually be installed. And some other interesting information, however, there are two fields which are specifically important or specifically interesting, which is the header MAC signature and the signature at the end. And it turns out those two fields actually represent the two protection mechanisms which are in place to prevent file tampering. So these two mechanisms actually guarantee that that the integrity of the file is valid. And so since we were interested in ways to actually get root access on the device, we took a deeper look into those mechanisms. So we start with the header MAC signature. This is actually an HMAC. So what you do is you just have a secret value, you calculate a hash over the header. And in order to verify this, you just do the usual thing. You zero out the field in the header, you calculate the hash using the secret, and then you compare the result. And if it doesn't match, you have an invalid pub file, so you just throw an error. Does anybody see a problem with such a mechanism in order to guarantee the integrity of a file when it comes to firmware updates? What's that? Exactly. I mean, to generate such a firmware update, the key is of course somewhere at the company, but you need to verify it. And in order to verify the integrity, this secret value, which is also used to generate those files, must be on the device somewhere. And it turns out it is, and it can be extracted. And we actually found the secret value inside this pubutils PowerPC binary. And if you take a look at the IDA screenshot at the bottom, you can see the secret value in the binary, which is some bytes at the beginning, and then the string "We are the champions," which I found pretty interesting. So having the secret value, we can now start to basically calculate our own MAC and just modify the header that way. However, in this case, it's much easier because in order to do that, you would typically just reverse engineer which kind of HMAC algorithm they are using, then do that. However, I said before, we can run this binary in QEMU. And just for testing, we modified the pub file and ran the verify command against it. And obviously, we get an error message like the MAC does not match, the pub header appears to have been tampered with. However, what I highlighted in red here is not what you would expect the MAC algorithm or the MAC value which is stored in the header, but this is actually the real expected MAC value. So what you can do is you modify the header, then just run this, get this error message, use this MAC value, put it inside your header, and you have a valid file again. So you probably shouldn't output such a thing in the error message. So we can basically circumvent this protection mechanism. However, as I said, there's another protection mechanism, which is this public key DSA signature, which was at the end of the header. And this one is actually calculated over the whole file, including the pub header. So it's not enough to just break the pub header protection, but you also need to break this mechanism in order to modify the file. And at this point, actually, we stepped back for a second because our initial goal was to root the device. And it turns out there are much easier methods actually to root the device instead of trying to tamper with the pub file. So we didn't do any further analysis on that mechanism. So device rooting. First of all, why do we want to get root on those devices? I mean, doing bug hunting is a lot easier. You can monitor processes, especially when we are talking about fuzzing. You want to have direct control over processes. You want to monitor for faults, stuff like that. And especially when it comes to writing exploits, it's much more comfortable if you have a debugger on the device and it can actually write your exploit on the real hardware, which is used in the final scenario as well. So it turns out there are actually two boot modes. So there's production boot mode, which is a normal thing. When you power the device on, it boots in production. However, there's an undocumented boot mode, which is called development boot. And development boot is probably used by Polycom internally. At least that's how it looks like. And it can still be enabled in the released firmware. And what happens if the device boots in development mode is there's an NFS client which tries to mount some developer workspace. And finally, a telnet server is enabled on port 23. And additionally, the root user doesn't have a password. So what you can do is you enable development mode, and then you can just immediately log in as root, and you have root access to the device. So the question is, how do we enable that mode? If you take a look at the startup scripts of those devices, you will see that there's a variable called devboot. And this is a uboot variable, which is checked, and if this variable is set, development mode is enabled. So actually, we can't modify that directly. But however, there are several flash-based variables. And one of them is called OTH boot args, which just are additional kernel parameters passed to the running or to the booted kernel. So what you can do is you just pass devboot equals something to OTH boot args, and it will automatically be set and will be respected in the startup script. So the question is, how do we modify those flash variables? Pretty simple. We just use a Polycom command shell, which is this command line-based administrative interface I talked about before. There are two commands, which is called print env and set env, which can be used to basically give you a list of all the variables and basically modify those variables respectively. So rooting the device really comes down to only two lines, which is this. So you connect to the Polycom command shell either via telnet or through a serial connection. You do set env OTH boot args, devboot equals bogus. Bogus is some kind of magic value which prevents the NFS client to time out, so it just is faster. And you reboot the device and you can log in via telnet. So pretty simple. However, after the device booted in development mode, it's not really the mode which it's running in when you want to run your final exploit, for example. For example, some of the end-user services are not running, the web interface is not started, so it's not really the mode you want to work in. However, it's pretty simple. You can just add permanent access. For example, we modified the INET deconfiguration for production mode. Add your own telnet server, save stuff, reboot, and you're good to go. Actually, to switch back to production mode, there's a convenient script lying on the device, which is called devconvert. So you just call devconvert normal, and the device will automatically reboot and boot in production mode again. And this script can actually also be used to do it the other way around. So if you somehow manage to run a command on the device, you can just call devconvert dummy or devconvert something, and it will automatically reboot the device in development mode, which is actually the second method we use to root the device, because you can just try to find a command injection in the web interface or somewhere else, and then use this command injection to actually root the device. And just as a demonstration, we actually used the command injection inside the firmware update functionality itself. So it turns out if you want to update the device, you upload a pub file via the web interface, and when it wants to verify this file, it actually passes this to a shell command, which is calling the pub utils binary again, but there's no input validation at all. So you can just upload a file called test logger pwn something, which will successfully execute your logger command. And to root the device, again, you just upload a file which calls, for example, the devconvert script. There are some limitations. So, for example, only the file name is used of the complete path. So you can't use slash characters in your command injection, but you can just use some kind of shell character substitution in order to circumvent that. You upload that file, and then you are basically in development mode again. So there are several methods you can root the device. However, the problem is these methods actually should be usable in the future, because we want to use them in order to conduct more research and give you the possibility to do more research. And the problem is all of those previous methods are based on vulnerabilities or bugs. And obviously these get fixed by the vendor. So what you could do, of course, is just try to find a new command injection, just try to find a new way of exploiting those devices. However, this is time investment, which we actually don't want to spend, because our main goal is to find vulnerabilities, real vulnerabilities, and not spend time with trying to root the device. So we came up with another basically idea, which is just based on the fact that we know all the old vulnerabilities. So what you could do is you just downgrade the device, because you can downgrade firmware versions, and then you exploit one of the known vulnerabilities, and you persist on the device. And once you did that, you just re-upgrade to the current version, and you have root access on the current version, and basically can do your analysis on the device with the current version. And since the downgrade feature is less likely to be removed, this might be an idea on how to conduct future research on those devices. So now that we got access to the device, we take a look at it from the inside. So as it turns out, it's a PowerPC based, some kind of embedded Linux system, has a U-boot bootloader, and it comes with all the basic standard binaries like busybox, wget. It also comes with a GDB server binary, which is handy because then we don't have to upload it in order to do remote debugging. There are several file systems, like we have a boot file system, the typical root file system. On HDA3, we have the log and configuration files, typical stuff. And we have a fourth partition, which is called the factory restore partition, which actually stores some kind of old operating system, which is used in the case if you want to completely restore the device, which might be a good idea to store your rootkit, maybe. So all the Polycom internal files are found in the Polycom directory, where you can find all the binaries, configuration files, stuff like that. So configuration files are pretty simple. So all the configuration settings you, for example, can change in the Polycom web interface are stored as single text files, basically, inside that directory. So it's pretty easy to find certain settings on the device or to modify them, for example. So there are two processes running which are more important than others when it comes to bug hunting. The first one is called the app main Java process, which is basically responsible for the GUI, and it also implements web functionality. For example, all the functionality available in the Polycom web interface is implemented in that process, and it also implements user authentication. So even if you log in via some command line based interface, the authentication is actually implemented in this Java process. And the second process is called Polycom AVC, which is some kind of more the low level process. And this one actually implements all the details regarding the signaling protocols. So the first process, the Java app main, app main Java process, all the jar files can be found in the Polycom bin directory. And of course, this process is running as root. And this one is actually a good place if you are looking for bugs in the web interface and you don't want to do only black box testing. You can basically decompile those Java classes and take a look there, because the web interface makes use of the light HTTP server with fast CGI, and all the CGI handlers are basically implementing the Polycom web CGI handler class. So it's pretty easy to actually find the code you are looking for. And as I said, this also implements the authentication. So if you want to try to find authentication bypasses or bugs of that kind, this might be a good place to look at as well. So the next process, the Polycom AVC process, is an interesting one. It's implemented in the AVC binary, which is a really huge non-strip binary. So it comes with all the symbols. And it's completely implemented in C. It's running as root. And And it implements all the low-level details regarding the signaling protocols and many other important and complicated protocols. So what could possibly go wrong, right? So this is the place to actually look for bugs with the signaling protocols. Just to give you an idea, there are, for example, more than 800 cross-references to string copy, more than 1,400 cross-refs to sprintf. There are no exploit mitigations at all. So if you find a bug, it's pretty easy to exploit it. And it's pretty easy to reverse engineer due to all the symbols. So now that we know a little bit about the device from the inside, about the major processes, we want to set up our WillenDev environment, which basically consists of setting up remote debugging. Because, as I said, it simplifies bug hunting. It allows you to more easily write your exploit. Actually, we tried to do debugging on the device itself. However, that failed miserably because trying to debug a 50 meg binary on the device, which really not a lot of memory, doesn't work. However, as I said, the device comes with a GDB server binary. So you just compile your own PowerPC Linux GDB binary and you can pretty easily do remote debugging. Actually, don't forget to specify the remote shared libs, otherwise you're running into some weird problems, which I learned the hard way. So this is how it looks like. So from inside the firmware directory, I'm basically attaching to the remote process running on the device, which allows me to do remote debugging. There's one thing which you need to take care of, which is Polycom's watchdog daemon. So they have some process running which tries to prevent crashes or tries to detect crashes and non-responding processes. And in that case, the device is rebooted. So if you're breaking inside your debugger and waiting for too long, the device just reboots, which is not really ideal. So somehow you must disable this daemon. So our first try was to just kill the process, which resulted in a reboot of the device. So that didn't work. However, it's pretty simple. The watchdog daemon is checking for a configuration file called watchdog disable. And if you create that file, it can be empty. On the next reboot, the watchdog daemon is disabled. So you need to do that in order to do proper debugging on the device. Okay, so now we have everything in place, so we can start to look for bugs, right? But what are we actually looking for? So I mean, as I said before, for example, finding bugs in the web interface is probably not too hard, and especially because there are many people to know how to do web application security. So it might be the first target for some people. However, our main goal was to find vulnerabilities in devices which are in a hardened environment. So we have firewalls in place, which should block access to the administrative interfaces. We have all the default settings configured to the most secure setting, like the call auto accept feature should be turned off, obviously. But as I said, those two protocols, H323 and SIP, they must be accepted, at least one of them, in order to use the device to do video conferencing. I mean, you could still disable them and use those devices as a pretty expensive heater or something, but I mean, in the normal case, one of those protocols must be enabled. And for our case study, we focused on the H323 protocol. So H323 is a pretty complex standard, and it consists of several different standards. And from a bug hunting perspective, there are some of them are more important than others. So this is just a list of some of them which should be considered when doing bug hunting. And without going into any details about those standards, what they have in common is all of them are used in the early connection setup phase. So which makes them pretty interesting for finding bugs, because you don't have to establish a full call and then try to exploit somebody, but you can actually use the initial packets to try to exploit the device. And we actually focus on the first protocol. So this protocol consists of several different messages. And each message consists of so-called information elements, which are basically just some some kind of information which is transmitted. And for example, the caller's identity is an example for an IE, which is just the name of the caller, which should be displayed at the other side. And there are other information elements like capabilities your device is able to support, stuff like that. This is an example from Wireshark where you basically can see a setup packet, which is the initial packet sent to the device when you want to establish a call. For example, you can see a display information element in the middle where it says display John Doe, which is just one of the many supported information elements. So how do you actually establish a call? Obviously, there are many messages involved. However, the first thing which happens is the client connects to port 1720. Then the first packet which is sent is a so-called setup packet, which indicates the desire to start a connection or to start a video call. And as it turns out, this packet is parsed at the remote side, even in the case if also the auto-accept feature is turned off, which is interesting. So those devices, those HDX devices, they have something called the call detail records, which is kind of a database which stores all the calls. So this includes successful calls, but also includes failed calls. And those entries are stored in a database based on SQLite on the device. And every record includes information such as the starting time of a call, the reason for failure, stuff like that. And also includes the remote system name. And this one is actually directly taken from this initial setup packet we are sending. So as it turns out, there is no input validation on this information element. So due to this reason, this leads to two different vulnerabilities. So the first one is a nice SQL injection, because the system name is used in the SQL statement to write the CDR entry. So in this case, we just sent a single setup packet where the system or the display name was set to SQL inject, which results in a SQL error message in the log. So this bug looks pretty nice because you get SQL injection with just a single packet. However, it turns out there are some little complications when it comes to exploiting that. Because if you take a look at the code, the SQL statement is actually passed to the SQLite 3 prepare v2 API function. And if you take a look at the documentation, it tells you that the SQL statement, only the first part of the statement is actually compiled. So if you try to append another SQL statement, for example, using semicolon, this wouldn't work in that case. The typical stuff like union statements, which you would think about, doesn't work either because it's an insert statement. So we played around a bit with it, but actually I couldn't find a way in the limited time we were looking at it to exploit that. Obviously, if you know a way or find out a way, I'm highly interested in it. But for the time being, we didn't find a way to exploit that. However, I said there are two vulnerabilities. And the second one is actually the one we were targeting. So the complete SQL statement, which is generated, is written to a log file. And they're using the VSN print function. And it turns out the complete SQL statement is passed in the format string parameter. So you get a format string bug. So you just send a single setup packet and you set the display information element to something which contains format specifiers like person n, and the device reboots because it crashed. However, our goal is not to crash the device, but obviously to take control over it. So we developed an exploit for the format string bug, and it turns out it's pretty simple due to no exploit mitigations at all. You basically use pretty straightforward format string exploitation techniques. There are some complications when it comes to details, but I mean, that's always the case if you're writing exploits, right? And basically how it works is we send a single setup packet, which we turn into our write for primitive. So a single setup packet will write 4 arbitrary bytes in memory at an arbitrary address. So we use that in order to basically store our whole shellcode in memory at a fixed address, because there's nothing like ASLR. Then we override a function pointer and basically let it jump into our shellcode. And in order to exploit this one, we actually used a pretty simple system shellcode, which basically where we write a shell command in memory and then execute this shell command. And that one just gives us a back-connect shell. And as I said, the AVC process, which we are exploiting here, is running as root, so we get a remote root shell on the device. So now we got root, which is nice, but we actually want to use those devices to do kind of espionage, and we want to control the device, and we want to control the microphone and the camera. So we were thinking about how to actually find the right code to do that. And one of the first ideas was to maybe take a look at the Polycom command shell, because this administrative interface has all the functionality inside. So it has functions to control the camera and do all the stuff we are interested in. So we started reverse engineering that binary. However, it turned out that the binary doesn't actually implement the functionality itself, but it makes use of some kind of internal IPC protocol, which is called XCOM IPC, which is Polycom's internal IPC mechanism. So we had the idea, okay, we could just use this XCOM IPC mechanism in our own payload to do what we want to do. So we reverse engineered the protocol, and it turns out it's pretty simple. So it's some kind of text-based protocol. The server for that protocol is running locally on port 4121, and it has some kind of asynchronous data receival mechanism. And basically, what you can do is you can reuse every command from the Polycom command shell in this XCOM IPC mechanism. So this is how it looks like. You basically connect to the local port 4121. You have to register your asynchronous data receival pipe, which you don't have to create before. So you have to just send the first line as it is. And then you can basically send all the commands from the Polycom command shell prefixed with a C colon. And obviously there are a lot of more commands, but you need to do some kind of reverse engineering to find out more commands. So after talking a lot about exploiting those devices, I have a small demo prepared, which basically shows how we are running the exploit. So this is a Polycom web interface, which just shows you that we are running on the version which was current when we did the research, which is 3.05. The IP address of the Polycom web of the Polycom device is 218. So on the right, you see the Polycom device. On the left, you see we first start our listener for the reverse connect back shell. And now we are running the exploit against the device. And now it's starting to send lots and lots of setup packets, which first store the shellcode in memory. And as you can see, we are sending setup packets, but on the right, you don't see any indication at all. So there's nothing like a window saying there's an incoming call or something, because we don't send any more packets. So it takes a while because it now stores the shell command we want to execute in memory. Now it's overwriting the function pointer, and as you see at the bottom, we get our shell. So it's running as root. So now we got access to the device on the right. And now we basically just use the wget binary on the device to receive our payload. Of course, in a real scenario, you wouldn't download a binary, but implement all the stuff in your payload running in memory to don't leave traces behind. But for our demo, we just download the binary and execute it on the device. So on the right, you still see no indication of any compromise. So that takes a while. Now we have to make it executable, and then we are running it. So the payload needs to receive some additional some additional information, some additional files. And no, you see, we. So it's just displaying some childish messages, playing some sound on the connected video, and basically moving the camera around just to show that we have full control over the device. So of course, in a real attack, you could, for example, listen in to what's happening in the room, do all kinds of stuff. All right. So I'll stop that. All right. So actually, before I close, a few words about the reporting process, because all the bugs we found, we reported them to Polycom, and actually they were pretty responsive. So during the last years, I reported lots of bugs to different vendors, and you know, if you do the same, you know, there are some vendors which really are not responsive, or they are pretty nice to you. They really tell you everything. You give them the information, and then they stop talking to you. But with Polycom, it was really nice. So the whole time we had really transparent communication. They told me all the details that developers were trying to do and tried to publish fixes just before the BlackHat talk. And they even offered me a test build so I could try to verify the bugs just before the official publication. So I would say other vendors could really learn a lesson from Polycom with this regard. So all of the bugs actually are fixed in the most current version, which is 3.1.1.2, which just got released yesterday, just in time. Yeah, and if you're running those devices, you should probably update, I guess. If you want to have more information about the exploit I have shown, all the details about the exploit are actually covered in the white paper. So if you're interested in that, just take a look at the paper. That's it. Thanks. Are there any questions?
How many times did you find those?
Actually, I spent maybe around a period of 2 months, but I didn't really work full time on that stuff. So it's hard to say, but yeah, maybe a month or two. Yeah. Yep.
Any idea if the same things happen in the Cisco environment?
Actually, I was planning to take a look at Cisco hardware as well, but it was a little bit problematic to get the hardware because those. Oh, I got pwned. But it turns out it was kind of complicated to get the hardware, especially because those kind of devices are pretty expensive. So you can't just buy one of them just to do some research. But I was actually planning to look into Cisco as well, but I didn't. All right, then thank you very much.